Go.
Hello everybody, I hope everyone's staying safe and healthy. So today our presentation is going to be on Abel and Abel Prize. My name is Megan Brown.
I'm Neusha.
And I'm Thershea. And this is Group 5. First off, we will talk about the history of Niels Henrik Abel. He was a Norwegian mathematician born in 1802 and died in 1829. He studied Newton, Euler, Lagrange, and Gauss's work and focused on algebraic equations, elliptic functions, and infinite series. Abel entered the University of Christiania in 1821, which did not offer a degree in mathematics. Unfortunately, he could not continue his mathematical studies abroad due to lack of public funds. Therefore, he remained at the University of Christiania for 4 years. Finally, in the summer of 1823, he got a chance to travel to Copenhagen to visit the mathematicians there, and in the spring of 1824, he was granted a government grant for 2 years, together with the promise of a journey abroad for another 2 years. He went to Berlin and finally began his mathematical journey, but he became ill and returned to his hometown in 1827. After recovering, he was unable to renew his grant. Therefore, he advertised in the newspapers for private pupils and took out a private loan, which he was never able to repay due to his short life. Now we will take a look at Abel's contributions to mathematics. At the age of 16, he presented a rigorous proof of the binomial theorem valid for all numbers. His first great mathematical achievement was his work on finding the roots of the fifth-degree equations during his studies in the University of Christiania, which was unresolved for over 250 years. He also worked on the theory of elliptic integrals. Most of his work throughout his life was sent to Berlin to be published in the Krell's Journal. A year and a half before his death, he submitted a series of treatises. The Krell's Journal was unable to publish them as rapidly as they were submitted. However, his most important work on the addition of algebraic differentials was submitted for the French Academy of Sciences.
As mentioned in the previous slide, insolvability of the quintic is Abel's first big mathematical achievement. To get started with, I just want to let you know that the fifth-degree equations was inspired from discovering formulas for quadratic, cubic, and quartic polynomials, respectively. We have a formula for finding the roots of quadratic polynomial, which we use since high school, and it's also written on this slide if you want to look at it. The formula to find the roots of degree 3, which is ax cubed plus bx squared plus cx plus d, requires solving a 3-equation 3 unknown to find the values for the roots. So as you can see, if we pick the roots to be p, q, and r, they can be found by the 3 formulas that are on the slides and are based on the coefficients. It is also possible to find 4 roots of a quartic in terms of its coefficients, but the formula for this is rather complicated and long. Abel considered the question of whether such formula exists for degree 5 polynomials. To show the proof that Abel did, we need to use some definitions and theorems to be able to understand it. The proof uses ideas from Galois theory. The Galois group is the group of permutations of a polynomial's roots. So it is a subgroup of the group of permutations in algebra. Solvable is when there exists a sequence of normal subgroups ending in the trivial group, such that the quotient of the consecutive subgroups are abelian, which means AB equals BA. There is a theorem that we use here, and it says that if a polynomial is solvable by radicals, that is, if general formula for finding its roots exist, then the Galois group is solvable. Another definition is Sn is the group of permutations of n objects. And there's a theorem that says that the group of permutation of 5 objects is not solvable, whereas for 4 objects and 3 objects it is solvable. Therefore, there exists a general formula for solving cubic and quartic, since they have 3 and 4 roots respectively, which gets permuted. However, when it comes to quintics, there exists quintics such as x to the power 5 minus 5x minus 2, which have the 5 objects of permutation as their Galois group, which is not solvable. And so the polynomial is not solvable by radicals. This is what Abel showed, that the general formula for the roots of a quintic can possibly exist.
The history of the Abel prize started after the death of Abel himself. In Abel's time, the field of mathematics was not popular. Regardless of his contributions to mathematics, he struggled to gather funds to travel for his studies. Sophus Lie was the first eager mathematician to establish the Abel Prize to honor Abel's memory and to promote mathematics as a science. Before Sophus died in 1899, he used his international prestige to gather support for establishing a fund that would award an Abel Prize every 5 years for outstanding work in pure mathematics. He was inspired by Alfred Nobel's plan for annual prizes that started in 1897, which did not consider a prize for mathematicians. He established supporting foundations in Europe which were tied to Sophus Lie personally, so when he died, the effort died too. Again, in 1902, King Oscar II became interested in a prize in Abel's honor, but his effort died as well due to political status at the time. Dissolution of the union between Sweden and Norway in 1905 put an end to any further plans. Further, his death, Abel's memory was kept alive in subsequent banknotes and stamp issues. The year 2000 was designated as the World Mathematical Year. National and international efforts aimed at the profession, schools, and society to create a broader appreciation for the importance of mathematics and science in today's society. Therefore, plans for a major international Abel Prize was reborn again. The group that worked to establish the Abel Prize was appointed in 2001, and the prize was established by the Norwegian government in 2002 on the occasion of the 200th anniversary of Niels Henrik Abel's birth. The importance of celebrating Abel's prize followed 3 tasks: to arrange a broad cultural commemoration, to raise a worthy monument in memory of the genius, and to establish an international Abel Prize. The Abel Prize is awarded to the fields of mathematics that are of extraordinary depth and influence. The prize carries a cash award of 7.5 million Norwegian krone, equivalent to around 1,045,000 Canadian dollars, and has been awarded annually since 2003. The Abel Prize contributes towards raising the status of mathematics in society and stimulating the interest around the world.
Here is a list of all prize winners from 2003 to 2019. All 19 Abel Prize winners received their prize at a very old age for their accomplishments in the past, because this prize is established to honor mathematicians' contributions rather than to fund their further studies. Out of all winners, we talked about Andrew Wiles, who is also the youngest prize winner, and he received it at the age of 62. We talked about him last week, and we are going to talk about John Thompson next week. Today we are going to talk about 4 other prize winners that are highlighted in purple. We picked John Pierre because he is the first mathematician to win this prize. And we picked Peter Lax alongside with John Nash because these two are one of the few prize winners who received their prize for their contributions in applied mathematics rather than to pure mathematics. John Nash also has a really interesting biography, and there's a movie made about him called A Beautiful Mind. Last but not least, Robert Langsland is a Canadian mathematician, and he's really famous in this century for his work and accomplishments.
So now we will look at the history of Jean-Pierre Sierre, who was born in 1926 in France. He was interested in both fields of chemistry and mathematics. He wondered if he should try to make a career out of mathematics outside of being a high school teacher. He became a research mathematician after he took the competition to enter the École Normale Supérieure and succeeded. Throughout his mathematical journey, Sierre made many contributions to algebraic topology, geometry, and number theory. Sierre received numerous awards. He was the youngest to be awarded the Fields Medal in 1954 at the age of 27. He also received Steele's Prize in 1995, the Wolf Prize in Mathematics in the year 2000, and many other honorary prizes prior to his Abel Prize. In fact, in 2003, he became the first Abel Prize winner. He won the Abel Prize along with other awards because of his important contributions towards solving so many problems in geometry and number theory. He played a major role in giving a number of mathematical topics their modern form, including topology, algebraic geometry, and theory of numbers. The next Abel Prize winner that we will look at is the history of Peter Lax, who was born in 1926 in Hungary. He is still alive today. In high school, problem solving in mathematics was specifically encouraged, which led to his great interest into calculus. Due to Hungary making close ties with anti-Semitic Nazis, making it difficult for Hungarian Jews like the Lax family, they left their country and emigrated to the United States in 1941. In 1944, he was drafted into the United States Army and spent 6 months at an Army training program for engineering. Unlike most others in his position who were shipped overseas to fight, he was sent to the Los Alamos Center in 1945 to participate in the Manhattan Project, building the first atomic bomb. He began working as a calculator operator but eventually moved on to higher-level mathematics within the project. Due to this position, Lax made important contributions to integral systems, fluid dynamics, shock waves, solitonic physics, hyperbolic conservation laws, and mathematical and scientific computing, among other fields. He was awarded the Lester R. Ford Award in 1966, the National Medal of Science in 1986, the Wolf Prize, the Abel Prize in 2005, and the Lomonosov Gold Medal. The Abel Prize specifically was awarded to Lax for his groundbreaking contributions to the theory and application of partial differential equations and to the computation of their solutions. The third Abel Prize winner that we will be talking about is John Forbes Nash Jr. He was an American mathematician who lived from 1928 to 2015. He made contributions to game theory, differential geometry, and the study of partial differential equations. He attended Carnegie Institute of Technology, initially majoring in chemical engineering and later switching to chemistry, followed by mathematics. After graduating in 1948 at the age of 19 with both a BS and an MS in mathematics, Nash accepted a scholarship to Princeton University in 1950. Nash earned a PhD with a 28-page dissertation on non-cooperative games. It contained the definition and properties of the Nash Equilibrium, which is a crucial concept in non-cooperative games that we will talk about later. Game theory was mostly focused on zero-game sum games, where there is both a winner and a loser. Last, Nash applied it to non-competitive games where everyone can, in a way, win. Most importantly, he was able to quantify that. This in his work that he did 4 decades earlier when he was a graduate student at Princeton, won Nash the Nobel Memorial Prize in Economic Sciences in 1994. He also worked in the area of real algebraic geometry. His work in mathematics includes the Nash embedding theorem, which shows that every abstract Riemannian manifold can be isometrically realized as a submanifold of Euclidean space. He also made significant contributions to the theory of nonlinear parabolic partial differential equations and to singularity theory. Nash taught at MIT, but his teachings was unusual and thus unpopular among students. Suddenly, in 1959, he began to have disillusions and was diagnosed with paranoia schizophrenia. This followed for 3 decades. Despite spending periods in the hospital because of his mental condition, his mathematical work continued to have success after success. In 2015, he won the Abel Prize for contributions to the theory of nonlinear partial differential equations and its applications to geometric analysis. A few days after winning, he died in a car accident.
Nash equilibrium that we talked in our last slide about it is a concept of game theory where the optimal outcome of a game is one where it would not be logical for the players to change their initial strategy, such that each player's strategy is optimal when considering the decision of the other players. Every player wins because everyone gets the outcome they desire. Nash showed that there is a Nash equilibrium for every finite game. Let's look at an example for Nash equilibrium. Imagine there's a game where there are two criminals facing jail time. They can either cooperate and don't snitch or betray and snitch. Looking at the chart, we can see that if they both cooperate, they will get €1 jail time each. But looking at it from one criminal's perspective, it's better for that criminal to change his strategy because then he'll get less jail time. And if the criminal does so, we will end up with one criminal having 3 years of jail time and the other getting 0. Now in this state, which is top right and left bottom of the chart, it's best for the criminal who's getting 3 years of jail time to change his strategy and get less years. And that will lead us to the last part, which is highlighted in the chart, where each get 2 years of jail time. In this state, it's not optimal for any of the criminals to change their strategies because they will just get more jail time. This is called Nash equilibrium, and in this game there is only one.
Langlands was born in British Columbia in 1936. He went to the University of British Columbia for his bachelor's and master's degree and received his doctorate from Yale University. Shortly after this, he was appointed to Princeton as an instructor. Langlands wrote a 17-page letter introducing a theory that created a new way of thinking about mathematics. It suggested deep links between two areas, number theory and harmonic analysis. They had both previously been considered unrelated. In 1988, Langlands received the first ever National Academy of Sciences Award in Mathematics, which was established by the American Mathematical Society. He also continued to win other prizes like the Wolf Prize, the AMS Cole Prize in Number Theory, the AMS Steele Prize, and the Shaw Prize. He is best known as the founder of the Langlands program, which is a vast web of conjectures and results connecting representation theory and automorphic forms to the study of Galois groups in number theory, for which he received his Abel Prize in 2018.
To summarize, Abel contributed to mathematics and had a big impact in his time, but he always struggled to gather funds to travel for his studies. The Abel Prize was established in honor of Niels Henrik Abel, and it was a difficult process which was not completed until 173 years after his death. Like the four mathematicians discussed, most Abel Prize winners received the prize at a very old age and mainly after winning multiple other prizes. This is because Abel Prize, unlike the other prizes, is given to honor mathematicians and boost their prestige rather than to support further studies.